Okay, again, welcome to the next lesson about mathematical modeling. Okay, now we come to almost the end of our lesson. Now we focus more on model fitting and experimental modeling. Well, in this the whole course, okay, in this particular topics, we are going to categorize this into three or at most four, okay, different video. The first video we will start to the in with the introduction. All right. Okay, so we try to introduce a little bit on what is actually model fitting. What's the difference between you fit the model or you interpolate the model. Okay, this is our main intention. Okay, the first one. So there are three situations involved in data fitting. All right. So it's either you can fit an already selected model into the data. Okay, meaning that you already have in your idea, in your in the back of your brain, you already decide the model type. It's already fixed. Okay, you know you are dealing with linear, quadratic, something like that. Okay, another way, you choose the most appropriate model from several alternative models. Okay, you want to see whether your exponential model or log model. Okay, so because it's especially on the polynomial, if you want to smoothen a little bit your reaction of the data representation. Okay, sometimes you can play around with polynomial of the power 3 or 4 or even 5, for example. Okay, so it's on how you're going to smoothen your valuation of your model. Okay, so that one is one thing. If you are deciding on already have already some hunch of your data that you would like to select, okay, we call that a model fitting. But if you are doing your making your prediction based solely on the data, okay, you don't have any hypothesis whatsoever regarding your data, you predict what intermediate future behavior just based on the data set that you already have. Okay, uh, but by the end of the day, please do not think first which one is correct. Okay, we are not talking about which one is the best, which one is correct. No, okay, that one we save it for later discussion. Okay, this one you just focus on the availability of the situational data and modeling. Okay, fitting or interpolation. Okay, or if you want to extrapolate your data or whatever. Okay, so this is just the technical fundamental of your further what you need to further know about these choices that you have. All right. So if you are talking about making prediction based solely on the data, okay, you are actually in a phase of doing interpolation. If you are familiar with cubic spline, your numerical method, for example, if you are already been dealing with MATLAB, okay, if you notice, those are all those are all some of the techniques that are able to make do with the interpolation concept, okay, so that you can make a good prediction. And if you notice earlier, okay, your main intention is to find the least error, okay, possible, okay, between your interpolation with the original data that you have, isn't it? Okay, so if you get the smallest error, then those interpolation that you choose. Okay, so that is the concept. All right, so that falls under interpolation. Uh, which one is the correct one? It all depends on the situation that you have, depends on the problem that you have, depends on the limitation that you have. Okay, as long as you are making your decision or assumption, not the assumption, your decision and your prediction are based from a sound judgment. Okay, sound judgment meaning that whatever ways you're going to model, then that's okay. All right, that's okay. People can improve upon your work. Okay, all the time. That is the progress that we would like. Okay, as long as you have the basis of your selected model that you choose. Doesn't matter. Okay, so we move forward. Okay, let's say this is the data that you have. All right. Oh, so by the way, if you notice on the bottom left side, okay, I put the name of the book and also the name of the author. Okay, this is also another good book. If you notice earlier, I adopted render book. Okay, so this one, you can look at Giordano and the gang. Okay, we have Giordano, Fox, and Houghton. Okay, this book is also quite extensive for you to understand mathematical modeling in a deeper level. Okay, okay, so you look at this one, the observation. You have five different dots. Okay, dot representing your data, your set of data. Okay, you are dealing with two set of data in a way, your x and also your y. So your data just representing your coordinate, for example. Okay, so how to move about? Okay, if you look at figure 3.3 versus figure 3.2, now you can see the difference, isn't it? Okay, the difference is 3.3, it gives you a line, okay, a line that follow through trying to reach the rest of your selected data set, but it is not that eager. Okay, at best it wants to the line must fit, okay, inside the data, okay, but it is not 100% eager to really want to be inside the dotted line. Okay, as long as your line fits just nicely, okay, fit just nicely, what meaning that it you don't have one data set that is so far off than your assumption. Okay, assumption meaning that your line that representing your fitted model. Okay, as long as you don't have the problem whereby two or three of your points divert so far away and then you match only two or three points and you are happy. No, that is not how model fitting works. Okay, in another occasion, okay, if you look at figure 3.2, that is not that. Okay, the concept is a bit different. If you notice, okay, in this figure, it looks like a complete match, okay, between your line and also your point. Okay, so this is the concept of having the first figure 3.3, the assumption of your best model, and figure 3.2, the interpolating, you interpolate your data using some form of the best model that you think possible. Okay, so in this case, they use spline interpolation, for example. Okay, so if you look at this one, suddenly you can just simply say, oh, if figure 3.2 are able to really get the whole points inside the line, why don't we just adopt all things using this figure 3.2? Okay, so in a real world or in a real application, this problem is not that easily solved. All right, it is not that easily solved. Okay, that's why you need to uh, understand a little bit which one the concept behind that. All right, so normally people are doing model fitting. Okay, the idea is that it is okay to at least get some sort of solution rather than you try to solve it by using interpolation and you don't get whatever result that you have. Okay, so which one you want? All right, so okay, why I said that? Because if you notice, you don't have that much polynomial function with you. Okay, because when you want to interpolate, you always normally try to get a smooth polynomial. Okay, but how many polynomial that you have? Okay, if let's say your data is so randomly scattered, if let's say you imagine randomly scattered, meaning that like okay, I try to make it a little bit like this. All right, so okay, if let's say this is your data. Okay, okay, so in the case your scattered data is like this, it is still a time series. Okay, but how can you able to smooth this particular data set into a polynomial? Okay, so it's a little bit tricky to get the good interpolation technique to solve this. All right. So this one, for example, you have to follow through some randomness inside that, and then you need to utilize a little bit different kind of derivation. Okay. To scrutinize doing this kind of partial differentiation, for example, to help you with the modeling in this certain part of the problem. Okay, that's why it is not that easy to simply put all into one basket and solve it by using, let's say, polynomial function, cubic spline interpolation, for example. Okay, it does not work that way. Okay, that's why we need to know also the fitting of a model, in a way. All right. Okay, so that is the concept of it. All right. Okay, now our main intention, okay, for your part two, later, you are going to discuss or study whatever happened with this. Okay, how can we make sure that the data that we do have fit the real, or not really the real, the assumption model, the constructed model, in this case your parabola here, fit the best way. Okay, this parabola fit with your data. And how you're going to construct this parabola? Okay, is it you can just normally, okay, put this visualization and do the parabola, or how you're going to match your parabola, for example, how you're going to get your a b parameter in your in your parabola model. Okay, y equals to for example ax squared plus bx plus c. So how you're going to identify your a, b, and c? Are you going to just simply put three data sets here and then put that into your parabola? Or how? All right. So that is what we are going to discuss later on. All right. Okay, so as this is an introduction, okay, we are going to expose you a little bit with some source of error. Okay, when you talk about modeling, the most significant errors that you normally get, okay, normally falls under these four category. It's either in your formulation errors. All right. Formulation error result from errors in the model to itself. All right. And then what does it mean by model formulation? Okay, the variable, sometimes we don't know, we didn't notice that we ignore certain variables. Okay, um sometimes we really tend to simplify. Okay, I also did make a lot of mistakes regarding this. Okay, since we would like to simplify most of our problem. Okay, and when we simplify, we keep on simplifying, we forgot that sometimes there are certain things that cannot be simplified. It's okay if you didn't get the valuation at this particular point in time, rather than you simplify and cut off as many things as possible, and then your model is really really simple, but then it does not reflect with the real data. Okay. mm. Okay. All right, so because everyone always want it to be very quick and very fast result, right? But in mathematics, doing the dirty work, you cannot have a good results by trying to make it quick. It's the same as don't ever go into a quick rich scheme. All right. Okay. So what about truncation error? What is that? Okay. Truncation error meaning that you actually it's quite similar to the round off error, meaning that you truncate certain it is not wrong, okay, it is not wrong, but you prematurely truncate, okay, a certain more important valuation. Okay, for example, the most simple example, if let's say you have a sign and then you want to calculate the sign function, okay, and you know when you calculate your sign function you want to make it into a valuation, so it's easier for you to transform, right, your sign function by using an approximation. Okay, so your approximation for your sign function is just like in here, right? But it is not just like this, isn't it? So this has negative ni, plus ni, and so on. Oh, sorry, if you forgot about that, you need to go back to your Taylor series. Okay, Taylor series. Okay. All right. So, but since you want to compute, okay, you stop until 1, 2, 3 only. Okay, you just eliminate the later valuation here. You have another x to the power of 7, to the power of 9, and so on. Okay, you just simply ignore it, assuming that it does not it does not affect your model assumptions. All right, so that is not. You will get the valuation, yes, but you need to consider the truncation error. And then another error, the round off error. If you notice why I said this one is similar, this one is because the idea is the same. You try to simplify things, all right? So in the round of error, if let's say you have, for example, this one third, okay, one third, you just simply use up until this. Okay, up until 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, up until 9 decimal place, which is not so right. Okay, so basically that is how, all right. And the measurement error, this one is difficult to detect. Okay, difficult to detect. The earlier one easier because it is still under your control. Measurement error difficult to detect. Why? Because it involved with the collection of data, meaning that the prior exercise. Okay, if you are an analyst, that's why I say it is outside your control. For example, because if let's say you sub your job, okay, your work, for example, this one, you don't want to uh, take all the data on your own, right? You cannot do everything on your own, so you sub contract your work. Okay, you collect your data, but other people collect the data for you. They don't know how severe the data that you want, all right? And they don't know, for example, if you are talking about getting the data on the time factor, for example, if you are actually want to model your queuing process, you by right, you yourself, you are very concerned on the time arrival, for example, until the very minute. But if you subcontract it to other people, you cannot expect they have the same passion than you, because they don't do the analysis, for example, they just do it for the pocket money, for example. All right, so the way they see it is that, not that I'm saying that you cannot trust people who collect the data. No, I don't say that. I'm just saying that the passion that they have is not the same as your passion as you yourself need to do the analysis. Okay, so if you yourself need to do the analysis, meaning that you know how severe it is if the data is not correct. Okay, but as a collector, as the one who do the data collection, they don't get the same pressure, okay, the same urgency that you yourself have. Okay, so that one you also need to take into account. That's why I say it is quite outside of our control. So I would recommend, if you need to do just that, to subcontract the collection of data, you need to really scrutinize the way you ask people to collect data for you. Why is it is important for you, so that they know the motivation behind what you want them to do. Okay, so these are some of the example. Another example, physical limitation of the instrument. Okay, for example, if let's say you need to check other people's blood pressure, for example, it's different, isn't it? All right. For example, the same people, the same level of ideal, I mean idle, okay, idle condition, okay, but in the morning it's not the same as you collect the blood pressure in the afternoon. Or maybe let's say suddenly they go out from the house, and then there's what traffic coming in. There's a car coming in, and then they just simply about to go out from the house, and then suddenly they get jumped. Okay, they are a little bit alert, so the pressure is a little bit different. Okay, but there is and your instrument cannot detect the real steady state that they have, you want. All right, so human error is another story. Okay, and if let's say you get the data, what you can do is how you're going to clean the data is another story as well. So these are some of the measurement errors. Okay, very difficult, especially if you need to collect a data. Oh, for example, like this year, we have a census 2020 census, Malaysian census data. You imagine our 33 million people, we need to collect all this data. So you imagine how many people involved in the collection of data, and how can we make sure that all the data are really streamlined. Okay, that's why if you notice, especially right now when we are having a lot of computer technology and so on, this year for example, the census data now, instead of they do it manually, they give another extra alternative for people to log in their information on the census online. Okay, so if let's say you have the opportunity to get the data in an online form, meaning that technical machine form, I would recommend you to do it online, or do it on a machine form, because you are able to reduce the measurement error based from human errors. You don't have that problem anymore. Okay, okay. But there are the negative side is that if let's say you want to see the not just on the paper results. Okay, if you want to see the reaction, that one you cannot get. Okay, because machine cannot measure the reaction. Okay, so that is the trade-off that you need to consider every time you want to subcontract. Okay, whatever analysis that you want to do. All right. Interesting, isn't it? Okay, so if you look at this data, um, how best to visualize? Okay, visualize the model fitting with the original data. Okay, you look at figure 3.5 and figure 3.6. Okay, if you notice at figure 3.5, you have 3 points. Okay, right now we have 4 points, A, B, C, and D. In figure 3.5, you have 3 points in the line. Okay, you have one point B outside the line, whereas in figure 3.6, you don't have any points inside the line. Okay, so which one is the right? We have for A, B, C, D. Okay, so which one is the right way to move forward? Okay, for example, are you going to choose figure 3.5 or are you going to choose figure 3.6? Okay, the plus point with figure 3.5 is that you get most of the data. Okay, you get most of the data, you minimize the sum of the absolute deviation from the fitted line, but what happened is that your D is so far off than your original assumption line. Whereas in figure 3.6, you don't have any points inside the line. This is how you're going to minimize the largest absolute deviation from the fitted line. Okay, what does it mean by you minimize the largest absolute deviation from the fitted line? Okay, you can see over there, there is no such thing, there is no condition as in your point D in 3.5. Okay, meaning that you don't have any so far large deviation. Okay, deviation meaning that the difference between this and this and this. This and this. Okay, so this is what it means by deviation. So you can see over here, what in figure 3.5, the main intention is to minimize the sum of the absolute deviation, whereas in figure 3.6 it is going to minimize the largest absolute deviation, meaning that you are not going to get the absolute deviation that is so far off than your fitted model. Okay, so if you have this kind of visualization, actually what you need, the idea, what you need to aim in your constructing of a model is just these three different ways. Okay, what you need is either you minimize the deviation, okay, but the first one you minimize the largest deviation, okay, as in figure 3.6, uh, or you can minimize the sum of all deviation, okay, or you can minimize the sum of squares of deviation. What are the difference actually between sum of all? Okay, the largest deviation is clear. Okay, but what's the difference between the sum of all deviation and the sum of squares of deviation? That one we are going to look at on part 2. You can see why we need to get creative and highlight the sum of squares instead of just the sum of all deviation only. Okay. Mathematics is always on the idea of trying to find ways to solve things. Okay, that's why you need to be very creative. You need to try to find ways, even though you see, oh, I cannot solve this. Okay, if you are a real mathematician, you cannot say that because you are going to be the one who's going to find a way to solve this. That's the main intention. Okay, for example, get if you get, for example, earlier you find the minimize the deviation sum of all deviation, and then suddenly you notice, oh, but I cannot solve it. Okay, and then you can just simply say, oh, never mind, I can just tweak this problem that I have, and then instead of trying to find the minimum of sum of all deviation, now I try to find the minimum of the sum of squares of deviation, so that one problem that involved with the second, the sum of all deviation is solved if you square the sum of all deviation. Okay, so that is how mathematician works. I hope you will work out the problem yourself as well. Okay, so this is the 1 million question. Okay, if let's say it is that easy, if we are able to easily transform all the data and fits just nicely, then you are able to become a good consultant in a way. Okay, so by the end of the day, our idea is can we transform the data to fit our needs? Okay, so common knowledge. Okay, what you have already studied from the very early in the very early semesters, if you notice, you already being bombarded with the linear line, right? Linear line. Everyone know linear line is y equals to mx plus c. Okay, even from your early schooling, for example. Okay, when you start to look at a mathematical model, actually you start with a linear function. That one is actually a model. It is a mathematical model. It's just that people didn't see it that way in their early years. Okay, if not, they feel like, wow, what is this, for example? Okay, but by the end of the day, linear function is just a model. Okay, a mathematical model, the model that you can really utilize for your own benefit. Okay, so our main intention, it is easier for us if you have a linear data. If you have a linear data. Okay, why? Because by the end of the day, we can make one line, fit them together, and then that's fine. Okay, we don't have to do much. Okay, we it's easy for us to find the intersect point for my y. Okay, it's easy for me to find the slope. Okay, meaning that if I'm able to find the slope and if I'm able to find the intersect of my linear line, definitely I know the real model, the real linear model. Okay, and then once I know the real linear model, then it's easy for me to project, meaning that I can forecast my future value based from my linear model. Isn't that heaven? Okay. But normally, what is it? Okay, our data is not linear, right? Normally, our data is not linear. So, how to make sure that we can utilize our main intention, okay, that my linear data, okay, if let's say I have a linear data, it's easy as I mentioned earlier, but as my data is not linear, how to do it? Okay, how to improve my stake? Okay, how to improve my chances to solve this problem? No worries, I can transform the data to be linear. Okay, so that is the concept. Okay, that is the mathematical reasoning behind all this construction of model. Okay, so when we transform the data, the main idea is that we want it to become a linear line. Okay, a linear function so that we can utilize. All right, so if let's say my um, my data falls under, if you look at the visualization, you see like, oh, this data looks similar to the exponent data. Okay, meaning that, for example, y equal to cex, ce to the power of x. Okay, oh, that's okay. That's okay, no problem. If you transform your data, you involve your ln. That's why we say that exponent and logarithm is a very close friend. All right. So if you transform your data by using your y equals to e to the power of x, you transform it. You transform it. You transform it into a logarithm function. That is what you get, right? Now your function of exponent function just become ln y equal to ln c plus x. Okay, because your x, earlier you have you have x ln e. All right, ln e just 1. Okay, so that's why you have that. Okay, so the idea, if you transform this, okay, if you transform this into this, the idea is that instead of you have y x. Okay, now your valuation will become this one. Okay, your y-axis now become ln y. Your x-axis now becomes ln c. Okay, your x-axis now becomes x. Okay, so the difference is in your ln y. Okay, so in this case, if let's say this is the value right now, okay, and then when you change that, it becomes something like this, or the other way around. Okay, doesn't matter as long as you know that you already force your valuation of exponent into a linear line. Okay, so this is one of the example. Okay, it is not necessarily just on the exponent. Okay, you can always transform whatever valuation that you have. uh, Play smart a little bit, be creative, and put it into a linear line. Okay, that can help you to solve that. Mm. Okay, now look at this example. Okay, we have four different points. Okay, your x and also your y. Okay, this is your data. Okay, and if you put your data inside this yex formulation, okay, you can see over here, if you put this is your y, okay, this is your ex in a sense, all right, because you can see over here, oh sorry, you can see over here, this one is y, so we assume we have this, all right, ex. So if let's say my x is 1, okay, my y would now become sorry, this is my 8.1 for my uh okay, like this, this is my y 8.1, and when you put your ex, your x1, okay, you do the calculator, is about 2 point something, all right, so it's somewhere around here, and so on. Okay, don't forget to include your x equal to inside your e. So put in the calculator. This is the valuation there. Okay, so if you have this, you can see here, you can actually find your c, isn't it? Okay, finding C is just using, for example, two different points. Okay, you can just choose this and this, this and this, this and this, for example. So you can use, for example, here, one line here. Okay, and then you can choose another valuation here. Okay, that's why you have this. C, your C, the first one is this value, 165. And then the second one is this value. It's about 60.1. Okay, so your valuation for your EX value now becomes, in this case, okay, this one, all right, yeah, it's a little bit off, all right. So let's say this one is 60, okay. So 60.1, and the second one is 20.1. Okay, so once you do the calculation a little bit, you have three. Okay, so look at this one, the difference between having the first raw data without you making any transformation or whatever, okay, compared to the same data, but now you are transform this into a linear line. Okay, so if you look at this, when you transform this into a linear line, you can see the changes of the valuation for your particular point now become this, and this. And if you notice, it becomes now a very straight line, isn't it? Okay, so based from this very straight line, okay, I try to I'm so sorry. Okay, let's say this is a straight line. Okay. Okay. So if you look at this one, you can just simply do a straight line, and then you can simply get the valuation for your intercept line over here. And you can see, oh, don't forget this one. Now instead of y, now your y-intercept is ln y, and then your x-intercept is just your x. Okay, so it's easier, isn't it? Okay, so in this case, your ln c now becomes 1.1, and then once you have ln c equals 1.1, you can just simply put inside, transform back into c equal to e to the power of 1.1, and you get approximately 3. Nice, isn't it? Okay, so it's easier, and then the illustration also seems very, very linear. Okay, so that is the meaning of transforming the valuation that you have. Okay, so that is how you're going to transform. Okay, this is just the idea. Always, but you look at the third point. Okay, okay, fitting a transform model to minimize the deviation may not yield a final model with minimum deviation to the original data. What does it means by that? Okay, it means that if you are not careful, okay, if you are not careful, there will be time for you to have a situational information, for example, like this. Okay, for example, like this. Earlier, you have this valuation in figure 3.9. Okay, it does not have a good way to move about. Okay, the dots are quite random. Okay, it's quite random. Okay, and then you're going to transform this valuation, this data set into a linear model. Okay, then that's fine. So in this case, your linear model now, the transform model now becomes this. Okay, your y-axis is ln y, and then your x-axis now is a little bit different than earlier example. You have 1 over x. But if you notice, right now, since you are talking about 1 point x, and then your data earlier, your data is a little bit scattered away, right? But now this data, since your x now is being forced into getting very small, the value is very small, then you're going to distort the data. Okay, you squeeze the data just in this particular quadrant. Okay. So if you have this data, all right, if you have this data, if you want to fit the data, if you notice, you cannot do much. All right, you cannot do much. You do some approximation, for example, like this. Okay, and then when you try to transform again to the original data, this is what you get. Okay, this is what you get. This is your earlier valuation. You can see over here your x 10, 30, 70 compared to your transform valuation point. All right, point 1, point 2, for example. And then see the this one. Okay, the valuation is a little bit off. Okay, the deviation over here is not that nice. It does not fit as nicely. Okay, so for example, like this, you mentioned over here, we would see that it fits the data relatively poorly. Okay, so these are the problem that sometimes occur during your analysis. That's why you need to refer back to the data from and fro, okay, to and fro, so that you don't get caught up with the unnecessary mistakes that you make along the way. Okay, if let's say your assumptions and your construction of data fitting does not fit just nicely, forget it. Okay, you redo the work, readjust your valuation, and sometimes you may consider other alternative, because if you are dealing with modeling mathematical model, or trying to transform certain realistic or application into mathematical model, try to be creative and try to force all the data and put it in a way that is nicer for you to investigate. Okay, so for the introduction part, we stop until here, and then later we are going to look at the analytic part. Okay, how can we calculate the deviation? So how to choose which deviation, okay, that we're going to adopt, and why do we need to adopt this deviation and why not that deviation, and so on. All right, so I hope you enjoy the video. I will give you more information on the next video later on. Okay, so all the best with your acquiring knowledge.